Next part we're going to explore here is getting a distance traveled. So what we did here was we explored the idea of finding the area of a strange, vague region that we don't have a formula for. Now we're going to do a different kind of application, which uses the same kind of a situation by finding the distance traveled. If we know the speed of something. Suppose we know the velocity function v of t of a car moving down a highway without changing direction, and wants to know how far it traveled between times A and B. The position function s of t of the car has a derivative v of t. We knew that from calculus 1, right? So the derivative of position is velocity. Let me see if we know another part of that. The derivative of velocity is acceleration. So to go the other way, if you go the other way, the antiderivative of acceleration is velocity, and the antiderivative of velocity is position, or displacement. If we can find an antiderivative, which they're going to call capital F of t, capital F of t, which is the antiderivative of the velocity v of t, then we can find the car's position function, s of t, by setting the position s of t equal to big F of t plus c. And y'all remember whenever we do an antiderivative, we got to put that plus c on the end of it. Because, let's just remember that real quick. What's the derivative of x squared? 2x. Okay. So what's the antiderivative of 2x? X squared. What's the derivative of x squared plus 7? Close. The derivative of x squared plus 7. What's the derivative of the x squared? 2x. What's the derivative of 7? 0. So the derivative of x squared plus 7 is still 2x. What's the derivative of x squared plus 1,000,000? Still 2x. So then the antiderivative of 2x is x squared plus something, plus a constant that we don't know. Constant might be 0. But it might be something else. So that's why we always, when we do an antiderivative, we put plus c on the end of it. All right. Graphically, that's like, okay, the slope of this is the same as the slope of this. It doesn't matter that a constant has been added to it to move it up or down. The slope is still the same. Okay. It's kind of like, all right, and here's a real life physics situation. If I'm getting my position function, and I know that I'm moving 2 meters per second or whatever, my position, my final position would depend on where I start. So if I'm moving 2 meters per second and I start here, I'm stopping here, that's going to be a different final position than if I started here and moved 2 meters per second. That's 2 different final positions. And the only difference was not the speed or the velocity. The only difference was my initial position where I started. And that's the plus c. All right. So we're saying that the position function of the car, s of t, that's the position function, is equal to this big F of t, which we've already been told the big F of t is the antiderivative of the velocity. So it's equal to the antiderivative of velocity plus some constant. that we don't know about. The distance traveled, so instead of getting the position, now it's saying the distance traveled. So if I go 2 meters per second from here, my distance traveled is the same as if I go 2 meters per second from here, the distance traveled. So even though my final position is different in each case, my displacement, or the distance that I've traveled, is the same in each case. Right? So the plus c won't matter when we're talking about just displacement or how far I've gone. It will only matter when I'm trying to figure out what is my final position. Okay? The distance traveled can then be found by calculating the change in position. So, in other words, the change in position is the position that you are at time B minus the position that you were at time A. So it's the position you ended up minus the position you started. The difference there is the distance you traveled. That's the displacement, or the change in position. Okay? All those are synonymous. But if I say the displacement or the change in position, that's pretty much synonymous with the distance you traveled, with the slight caveat of if you change directions, then that's not going to be the same. But it told us at the beginning that it didn't change directions. So that's why we can kind of talk about all that as the same thing. All right, so that's the same thing as saying f of b minus f of a. Now, why is that the same? Because in each case, if I take s of b, and if that's the case, it's going to be f of b plus c, and I do s of a. You don't have to write it this down. It's going to be f of a plus c. And then if I take the difference, in these two things, it's going to be f of b plus c minus f of a plus c. And I distribute that minus sign. This is just algebra skills here. Distribute the minus sign. That becomes negative. That becomes negative. So now, what cancels? The c's cancel. So that's why the c's don't matter whenever you're finding the displacement. And you just end up with f of b minus f of a. Because the distance traveled in either case is going to be the same. Doesn't matter where you started from. The distance that you went is the same. Okay? So that's how they can say that the change in position is just going to equal the difference in the antiderivatives. Okay? If the velocity function is known only by the readings at various times of a speedometer on the car, then we have no formula from which to obtain an antiderivative function for velocity. So what do we do in this situation? So in other words, it's saying you don't have a velocity function, a nice polynomial that we can do the antiderivative formula on. You only know the velocity readings at discrete points in your travel. So like driving along, I look down, okay, I'm going 20 miles per hour. Driving along, I look down again, okay, I'm going 22 miles per hour. Driving along, look down again, okay, I'm going 21 miles per hour. So you just know that at one second you're going 20, at another second you're going 22, at another second you're going 21. So you just know these various values of the velocity at random points. So what do we do in this situation? Can we figure out the distance that we've traveled, or at least approximate it? When we don't know an antiderivative for the velocity function v of t, we can approximate the distance traveled with finite sums in a way similar to our estimates for the area discussed before. We subdivide the interval a to b into short time intervals on each of which the velocity is considered to be fairly constant. Then we approximate the distance traveled on each time subinterval with the usual distance formula. So if you know your velocity, like if I was going, let's say I was going 2 meters per second, and I did that for 5 seconds, then the total distance I traveled would be 2 meters per second times 5 seconds would give me 10 meters. The velocity times the time would give you the distance. Okay? let's see if that's, so we take our full time interval, let's say if the time interval is 20 seconds, we're going to divide that 20 seconds into smaller subintervals. And I don't know how many. It could be 1,000 subintervals. It could be 5 subintervals. Kind of like how many rectangles do we want? Kind of like that. Then we approximate the distance by doing the usual distance formula we just said. Distance is just the velocity times the time. And then you add up all those results across that whole interval. So suppose the subdivided interval looks like that. All right, so from time A to time B, you're subdividing that full time interval into smaller time intervals, dividing it by delta t. So delta t would be however many intervals you want. It would be b minus a divided by that, right? So if this is 20 seconds and we want 4 rectangles or 4 time intervals, we would divide it by 5. I'm sorry, we would divide it by 5. So each little delta t would be 5, and we would end up with 4 subintervals in that case. Kind of with me so far? Okay. With the subintervals all of the equal length delta t, pick a number t1 anywhere in that first time interval. So if this was 20 seconds, if this whole thing is 20 seconds, and we wanted 4, 1, 2, 3, well, I think I can actually fit 5 in there. So 1, 2, 3, 4. So there's 5 time intervals. Then each of these delta t's would equal 1, 2, 3, 4, would equal 4. And so I would pick T1 somewhere in there. It doesn't matter where. So if this first little delta t is 4 seconds, then T1 could be anywhere between 0 and 4. T2 could be anywhere between what and what? 4 and 8. T3 could be anywhere between 8 and 12. We pick a T4 could be anywhere between 12 and 16, and a T5 could be anywhere between 16 and 20. Okay, and then we would have something in each of those little rectangles, or each of those little time intervals. All right. If delta t is so small that the velocity barely changes over a short time interval of duration delta t, then the distance traveled in the first time interval is about the velocity at that time 1 times the time that it went that velocity. So that means, like, in this 4 seconds, I look down at my speedometer. Somewhere in that first 4 seconds, let's say at 2.8 seconds, I looked down at my speedometer and I was going, let's just say 5 meters per second. And so I'm going to make an assumption that within those first 4 seconds, that my velocity did not vary very much from 5 meters per second. And so if I went 5 meters per second that whole time, and I multiply that times the 4 seconds, then during that first time interval, how far did I go? 20 meters. All right, and then in this second time interval, let's say I looked down during the second time interval and I saw that I was going 6 meters per second. And again, I make the assumption that 6 meters per second is going to be somewhat close to the velocity that I went that whole time during that next 4 seconds. And so I multiply that again by the 4 second time interval of that next 4 seconds. And how far did I go then? 24 meters. And I look down again, and let's say I was going 3 that time. Again, times the 4 seconds. It would be 12. And I get all those. Let me just go ahead and finish it up. Let's do 5 again. And how many did I have here? I had 5. let's say I look down again and I was going, let's say I was going forward that time. So the total distance that I traveled then over that full 20 seconds would be equal to what? I would do what to find it? Add all those up. I would add the distance I traveled in the first 4 seconds with the distance I traveled in the second 4 seconds with the distance I traveled in the third, and the distance I traveled in the fourth, and the distance I traveled in the fifth 4 seconds. And all that added together will be the total distance I traveled over the full 20 seconds. And that is very related to, this is the area of the first rectangle plus the area of the second rectangle, on and on until I get the full area. So it's like that velocity is the height, that time is the width of the rectangle. So it works the exact same way. And so if you can see how that's going to work as an application of calculus to physics, that if you have a velocity function that is some kind of a strange function, we're still going to be able to get the distance traveled by doing the calculus thing to it. And the height is going to be that velocity, and the width is going to be that change in time. And it's going to relate to an area. It's going to give me the distance. So this is just saying the same thing we just said. The distance traveled would be approximately equal to the velocity at time 1 times the delta t, that's the full time interval, little sub-interval here, plus the velocity at time 2, plus delta t, which is the width of that time sub-interval again, plus dot, 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 all the way down to however many velocities I took, however many times I looked down at my speedometer. All those added together, where n is the total number of those subintervals. Our example 2, the velocity function of a projectile fired straight into the air is this. All right, 160 minus 9.8 t meters per second. Use the summation technique just described to estimate how far the projectile rises during the first 3 seconds. How close do the sums come to the exact value of 435.9 meters? All right, the solution. We explore the results for different numbers of intervals and different choices of evaluation points. Notice that f of t is decreasing, so choosing left endpoints gives an upper sum estimate. Choosing right endpoints gives a lower sum estimate. All right. So what is our full time interval for this problem? 3 seconds. So maybe we would just divide that into 3 subintervals of how long would each subinterval be if I divided it into 3 subintervals? 1 second each. Yep. Okay. So if you did a left hand approximation, then you would start at 0. And then the next one, if we did 3, the next one would be 1. And the next one would be 2. And that would give us our 3 subintervals. If we did a right hand approximation, then instead of doing 0, 1, and 2, we would do 1, 2, and 3. Am I confusing you yet? Or are you feeling good? Okay. If we did the 0, 1, and 2, we're going to end up a little bit too much. And if we use 1, 2, and 3, we're going to end up a little bit too small. Okay, so notice that when we do that, so it gave us the velocity. Let me just show you how this is working. 160 minus 9.8 t. So then we would get and we're doing this from 0 to 3 seconds. So we would get the velocity at 0. Which would give me 160. And I would have to multiply that by the time. What is the delta t that we're saying we're going to use here? It's a really easy one. Not 0. 1 second. So delta t is just 1. So then the velocity times the time will just be 160 times 1. Okay, so the distance traveled in the first second would be that right there. It would just be 160. The velocity, the distance traveled over the second, so between second 1 and second 2, if we're using the left-hand rule, we're just going to plug in 1. The velocity at time 1, so 160 times 9.8 times 1. Alright, and that's this part. The delta t is again just 1 second. So that would be what? That would be 150.2. Y'all see if I did that right. What's that? 160 minus 9.8. 150.2, I think. Times 1 is just 150.2, so that's that guy. And then the third rectangle, or the third distance traveled, is 160 minus 9.8 times 2. Again, the delta t here would be 1. Let's see, what's 150 minus 9.8? That's going to be 140.2, 140.4. And that's that. Y'all know I'm not very good at subtracting and multiplying, so if I messed up, sorry. But that's why I used that there. So that plus that plus that gives me that the total distance traveled over those 3 seconds is 450.6. The problem with that, though, is it wasn't going 160 that whole first second. Like, basically, it's like if I'm throwing something in the air, during that whole first second, if I'm throwing it in the air, it's going slower and slower. You see what I mean? Like, if I throw this thing in the air, it starts out going a certain speed, but it's slowing down as it's rising, right? So during that whole first second, it's not going 160 that whole time. It's going 160 at the beginning of the first second, but it's going slower and slower than that the whole time. Which is why this is going to overestimate the distance traveled. And then if you use a left-hand rule, a right-hand rule, then instead of using the points at 0, 1, and 2 for that whole subinterval from 0 to 3, instead of using those three values, we're going to use 3, 2, and 1 because we're using the right-hand process. So it's like I have a rectangle here, and a rectangle here, and a rectangle here. All right. And so when you do that, you get this. But again, that's not going to be correct. It's going to be an estimate, but that's going to be too small. So then, the next thing they're saying you could do is, instead of dividing it into 3 subintervals, you could get a better approximation by dividing it into 6 subintervals. So this time, if we divided it into 6 subintervals, I'm not going to do the whole thing, I'm just going to do enough to give you the idea. If I divide it into 6 subintervals, I've got a 3-second window here. But if I divide that into 6 subintervals, what is going to be the width of each subinterval? If I divide it into 3, it's going to be 1. If I divide it into 6, everything's going to be a half, right? The width of each subinterval is going to be a half. One, 2, 3, 4, 5, 6. I didn't quite make those wide enough, but you get the idea. So then I would do the velocity at 0, the velocity at a half, the velocity at 1.5, the velocity at 2, the velocity at 2.5, and then that would be that would give me all the rectangles I need. And each delta t in this case is not going to be 1, it's going to be a half. And so like that times a half, plus that times a half, plus that times a half, plus that, all added together is going to give me my new estimates for the distance traveled. Again, it's going to be too small. If I do from the right, I'm going to do it at 3, at 2.5, at 2, at 1.5, at 1, and at a half. But then that's going to be too, I think that one's too big, this one's too small. Okay, you get the process, how this is happening each time. All right, they provide a table for us. They went all the way to 192 subintervals. So that they broke those 3 seconds up into 192 sections. And when they did that, they got an upper sum of 436.13 and a lower sum of 435.67. So we could then reasonably say that it went probably about 436 meters, somewhere between those two values. Is that helping you on your homework problem so far? Let's just look at the homework problem before we continue. Let's look at the homework problems and make sure we know what we're doing on them. Says this first one says use finite approximation to estimate the area under the graph of 9x squared and above the graph of f of x equals 0 from 0 to 16 using a lower sum with 2 rectangles of equal width, a lower sum with 4 rectangles of equal width. Okay. What does 9x squared look like? Is it increasing or decreasing? If you start at 0 and go to 16, it's increasing. It's going to be something like that, right? So we're approximating the area in here. So if you want to get a lower sum, would you want to do the left-hand rule or the right-hand rule? Right. If you do a left-hand rule, I'm sorry, I think I said that right. If you are wanting to get a lower sum, you're going to need to do a left-hand rule. Because if you do a left-hand rule, you start here, and like that would be your first rectangle. And then here, this would be your second rectangle, your third rectangle, and your fourth rectangle. So if you want to get a lower sum for parts 1 and 2, you're going to have to do a left-hand rule. And if you want to do an upper sum, then you're going to start on the right side, because that's going to give you rectangles that are outside of that bounded area. Does that make some sense? Do you want me to continue doing this problem, or you think you know how to do this problem? Keep going? Okay. So if we're just doing a lower sum, we said we were going to use the left-hand rule to do a lower sum, right? With two rectangles of equal width. On my problem, it goes from 0 to 16. Your problem may be use different numbers than that. But mine goes from 0 to 16. All right, so if I'm going to divide that into two rectangles, then what's going to be the width of each rectangle if I divide that 16 just into 2? 8. So, my first rectangle, the height is going to be f of 0, which is going to be 9 times 0 squared, which is 0. And my width, or we can say delta x, is equal to 8. So my area for my first rectangle is going to be 0 times 8, which is 0. That's this guy right here. Okay, my second rectangle is going to start where this one stopped. My first rectangle stopped at 8, so my second rectangle is going to start at 8. So it's going to go up to the height of the curve at 8. So my height is f of 8. Which is pretty darn high. It's 9 times 64, it's 640. 964. $76. I'm not going to do that right. I'm going to cut myself when we cut that. And the width what's the width of my second rectangle? Yes. It's again 8. The width is going to be the same the whole time. Whatever your width is, it's going to be the same width for all the rectangles. And so, the area of that second rectangle is going to be 576 times 8. Which is that. So my total approximation then is going to be the area of the first rectangle plus the area of the second rectangle, which in this case is 0 plus that, which is just that. That would be my answer to part 1.
So is your first, like, is that answer 0 for yours?
For part 1? No, my answer to part 1 is the sum of both of those rectangles. See, that's my first rectangle, and then this is my second rectangle, and so that area plus that area is the total approximate area. So in this case, it's 0 plus 4608, which is 4608. Okay. If I'm doing part 2, are y'all ready for that? Or you want me to pause it for y'all to get there? You good? Okay. If I'm doing part 2, I'm dividing it into 4 rectangles instead of 2. So again, if I'm doing a lower sum, I'm starting on the left. So my first one starts at 0, and it's going to go. If I'm dividing this region into 4 rectangles, you know, the whole thing is 16, so if I divide it into 4, what's each width going to be? Yeah, 4. So my first one's going to go to 4. And then my second one's going to start at 4 and go to 8. My third one's going to start at 8 and go to what? To 12. And then my fourth one's going to start at 12 and go to 16. So I've got these 4 rectangles instead of the 2. I've got 1, 2, 3, 4 rectangles. Okay. One more thing to tell you before you go is we mentioned this displacement versus distance traveled. Those are the same thing. My displacement and my distance traveled is the same thing unless I change directions. If I change directions, I'm still adding to my distance traveled, but I'm subtracting from my displacement. So if I throw a rock up and it goes up and comes down, then the displacement is only that far. But the distance traveled is all of that distance plus all of that distance. You see the difference? So how do you handle that when we're doing these problems? It's pretty simple. Instead of doing velocity, you're going to do speed, which is the absolute value of velocity. So like if you were going 20 meters per second for 5 seconds, and then you went backwards, so you're going negative 20 meters per second for 5 seconds, and here you went 100 meters per second. I mean, you went 100 meters, and here you went negative 100 meters, so your displacement would be 0. You'd be back where you started. but your total distance you travel would be adding the two instead of subtracting them. So all you do is instead of doing a negative 20 for the velocity, do the absolute value of the velocity and it'd be a positive 20. And then that would be 100 and another 100 added together would be 200. So you do the absolute value of velocity to get to this, to make, if you change directions is when it matters, to get the displacement versus, to get the distance traveled instead of the displacement, if that's what it's asking for. All right, and we'll leave it at that. You're going to need to finish 5.1 homework and do 5.2 homework. Monday we don't have class, so I'm going to give you some sort of a video learning experience for them. Both of those will be due next Wednesday night. See you next time.